Okay, hello everybody to today's ISGC seminar. Today's speaker is Alexander Vikman. He did his PhD in 2007 at the Ludwig Maximilian University in Munich. And since 2015, he is a senior researcher at the Institute of Physics at the Czech Academy of Sciences. Thank you very much for giving this talk. And he will talk to us about ghosts. And with that, hand over to you. The stage is yours.
Well, Torben, thanks a lot for invitation. Thanks a lot for introducing me. I'm trying actually to put OK into the bar with this record, like whether I agree to be recorded. But the problem is, just give me a sec. It seems that I need to agree on that and then go ahead. So it's my great pleasure to entertain you in this, I would say, intergalactic seminar on gravity and cosmology. So feel free to interrupt at whatever moment if you want to ask something. I'm not sure I actually will be able to see your reactions. So either just switch on, unmute yourself, or maybe raise a hand so that maybe Torben would then tell me. Okay. Sorry?
I will monitor the chat, so I will tell you when somebody asks.
Great. Thank you. So I will tell you everything what you need, or maybe don't need to know about ghosts. And I will tell you what actually ghosts can do. What does it there? So actually, I was inspired by this fantastic movie. As you see, it's the movie which was called Ghosts Cannot Do It, Can Do It, okay? So it's a very interesting movie. I'm not sure I recommend you to watch it because you see, this film was panned by critics and was a box office disappointment. And actually, Donald Trump appearance as himself earned him a Golden Raspberry Award for Worst Supporting Actor. I'm not sure he's a supporting actor anymore. Also, Trump and Damian were both, I think Damian is the actress there, were both nominated for Worst New Star, but lost to Sofia Coppola in The Grandfather Part 3. And the film also won the Worst Picture, Worst Actress, and Worst Director awards. I think this is a fantastic result. So, I got inspired. So, therefore, let's make ghosts great, or if you want, stable again. Okay, so to be, so you see, Torben, that's why I prefer this title. So to be on more serious side, so this talk is based on the following two papers. One paper is the one which you published already quite a while ago, it's like almost 3 years ago, in PRL with Cédric Defayet and Shinji Mukayama. And another one is the one where also our team was joined by Aaron Held. And, Held in German is hero. So I think he has done a heroic effort to improve our numerics and doing things like that. So this is other paper, larger than the first one, with more models, more details, and so on. So you can read this other one too, if you want. So if you want to spare time, you read the first one. If you want to see more details, you read the second one. So more seriously, my kind of motivation comes also with this paper by late Stephen Hawking and Thomas Hertog. And the title of the paper was Living with Ghosts, okay? And if you read there what they write as the first sentence in the abstract, so perturbation theory for gravity in dimensions greater than 2 requires higher derivatives in the free action. And then they write that higher derivatives seem to lead to ghosts. And after that, they specify states with negative norm. That's not what I like. So I don't like states with negative norm. I like normal Hilbert spaces, right? So therefore, I'm not considering states with negative norm, and therefore I'm doing something similar, but it's still not that kind of living with ghosts, okay? So what are ghosts for this talk? So ghosts are dynamical degrees of freedom with negative mass. So if you want, they have opposite signature, or if you want otherwise, their kinetic energy is unbounded from below. Okay. And of course, after that, you can be very skeptical. You can be like these dudes here, and you can say, okay, why should we care? And, out of this skepticism, I could also quote a senior colleague of mine who at one of the conferences said that, okay, no way to live with ghosts and no way to live without ghosts, okay? So you should not be that skeptical. You should be more optimistic like this lady below these three guys, okay? Good. So why are we interested in ghosts? So first of all, there can be interesting cosmology, okay? So one could have phantom dark energy, which is actually super accelerated universe with Hubble parameter, which is growing with time, okay? So this is really like superinflation, if you want, okay? But that would allow you to solve maybe for initial conditions and things like that. On top of that, it can be dark energy, and this is interesting. So now the situation with dark energy is that this growing Hubble is not actually excluded by data. Even worse, some data will tell you that it's slightly preferred, not statistically significantly, but slightly preferred. And the good question is whether you should look at parameters for such a thing at all. Okay, that would of course change your priors, that would change statistics. So there is some practical meaning of talking about ghosts, whether they're relevant or not for dark energy. Again, I said you that would allow you the super acceleration to have a bouncing universe in the early stages. And the superinflation would actually result in also blue spectrum of gravity waves. So that could be also actually interesting for some phenomenology, as we are living in the gravitational wave era, right? So this is like a kind of, if you want, semi-practical aspect. Then there is more kind of ideological questions that high derivative systems, they have ghosts due to their Ostrogradski theorem, which is really a fresh theorem from 1848, okay? So basically this paper from mid-19th century provides you a way how to write Hamiltonians for systems which have high derivatives. Of course, Ostrogradski himself never cared about whether these systems have positive energy, negative energy. It's not actually there, but it's just how to write Hamiltonians. And you see, it's an ideologically interesting question because normal dynamics is somehow second order. Okay, normal dynamics comes from Newton's equations, and Newton's equations are second order equations. However, in nature, there could be potentially systems with high derivatives. And you see, not only in nature, actually, even in our computer technology, we use what is called CHUAS circuits. And these are, if you want, random number generators, which are using chaotic dynamics, and they are based on third order equations, on so-called jerk equations. And you see, so these are the things which you can model using electric circuits. And it's very important because if you want dimension 3 is the lowest number of dimensions when you can have chaos. But of course, if you have third order equations of motion, why not to have even higher order equations of motion? Then we are coming to the next point, which is more related to what Hawking and Hertog were writing. Namely, you can write a model for gravity which is renormalizable, okay? For that, you start with normal Einstein-Hilbert terms, the first terms there. And by the way, I don't have a pointer somehow in my Zoom, and I don't know how to arrange it, but I hope you see it. So first term is m Planck squared, so that's the standard Einstein-Hilbert term. And if you supplement this term with the Ricci scalar squared, in that case, you are in what is called Starobinsky gravity or Starobinsky inflation. And then you can supplement it with a third term, which is actually wild tensor squared. Okay. So what is interesting? So following actually Ostrogradski theorem, adding a Ricci scalar squared adds you new degrees of freedom. Okay. How to see it? Well, actually, there is already a second derivative in the Einstein-Hilbert, but the second derivative enters linearly. So therefore, it's not important for any dynamics for changing order of equations of motion. So at the end, Einstein equations are normal second order PDEs. If I write R squared, then they are not anymore second order PDEs, but I can reformulate them as second order PDEs. And basically, I could manifestly see one healthy new degree of freedom, which is called scalaron. But interestingly enough, so Kellogg-Stelly in 1977, he pointed out that if you write this wild term squared, in that case, so wild tensor squared, in that case, you can renormalize gravity. So there's no problem. And the problem is that, of course, wild square term would give, if you want, Gauss partners for all your normal gravitons. So in that sense, your system would have Gauss, okay? And it would be nice to understand what to do with this quadratic gravity, especially in light of the following observation that the first two terms, which is called Starobinsky inflation, or sometimes people call it Starobinsky gravity, perfectly well describe all observational data related to inflation, okay? And interestingly enough, the coefficient there for Starobinsky inflation, this coefficient alpha is like 10 power 11. So it's quite a big coefficient. And the question is, why this beta is not of the same order? So what is beta? It's not like, basically people don't know what to do with this. It's an interesting puzzle, definitely worth understanding better. Then, and it's also related to observations, as you see. Then the equations related to entropy and thermodynamics, because you see, if you allow for negative energies, then it's a question what to do with temperature. And of course, entropy, statistically defined, should be always positive definite constant, right? So therefore, it's a good question what to do with whole thermodynamical description. And then you see our basis of civilization, right? Of modern technology is related to a very simple, very, very fundamental fact that actually electromagnetic forces and almost everything what is around us is either gravity or, in most cases, for small scales, it's electromagnetic forces. So these electromagnetic forces are actually screened, okay? And this is, of course, only possible because we have positive and negative charges. So the question is it possible to screen gravity? And this is very deep question. So it would be very important to understand. And of course, if you can screen gravity by introducing negative charges, that would allow us to do a lot of new technological things. And if you are more modest about screening gravity, like not completely, but let's say screening only some parts, then it's a question whether it's possible to screen cosmological constant or energy of quantum vacuum. This is also kind of related. And, you know, there were old models introduced by Andre Linde, for example, then later by Randall, by basically Sandrum and company. It's like, one, if you allow for Gauss, you can screen cosmological constant, and that's interesting. And then you see, if you allow screening gravity, then you open up Pandora box. So in particular, you can have interesting exotic compact objects like wormholes and many other interesting things can happen. And then to finish this long list, I could mention another motivation that you see there is an interesting question whether gravitons can be massive at all, okay? And the story is well known. So already in the early 70s, it was showed that if you start from linear theory, basically from Fritz-Pauli, then if you go non-linearly, then you get another degree of freedom, a fixed one. on top of 5 which are needed for spin 2. And we get a 6th one, and the 6th one is non-linear, it's strongly coupled, but it's actually a ghost. It's what's called Boulevard Desert ghost. And it appears in normal series, like basically with necessity. However, more recently, there was this construction by Deram, Gebadadze, Tolly, when you can avoid this 6th degree of freedom. And you have only 5 degrees of freedom. And the problem there is the following, that these 5 degrees of freedom are healthy normal degrees of freedom on Minkowski background. But if you change the background, then suddenly you will see, for example, in cosmology, that 2 of these degrees of freedom are not healthy. They are kind of ghosts. Okay? So therefore, if you want to play basically with masses of the gravitons, you better think about ghosts too. Okay, and what to do with them. Good. So this is basically my motivation. If you have other interesting examples or questions which one could address potentially with ghosts or where ghosts could be relevant, please let me know. I will be happy to maybe consider them or include them in the list. So now let me start from this gentleman. And this gentleman, you probably would not recognize him, but his name was Giuseppe Ludovico de Lagrange Tournier, okay? Or as we know him, Lagrange. So Lagrange was studying some stability issues, and later it was called Lagrange stability. So what is Lagrange stability? It's a kind of very primitive notion that motion is just finite. So it should be bounded in the phase space. Sometimes you can say that it's global stability if this boundness in phase space is applicable for whole phase space, okay, of your model. Of course, it's an idealization, because this system should interact with some other systems, and actually in reality you never know whole phase space. Also, by very large values of coordinates of fields, this description most probably breaks down. So therefore, you know, to consider global stability, it's quite an overstretch, but it's nevertheless a mathematically important issue. And then there is another gentleman, and the name of this gentleman was Lyapunov, and Lyapunov introduced what is called Lyapunov stability. So this is a local notion. So it is about not like basically property of motion in total, but it's a property of a motion for a given solution. And usually people study as solutions equilibrium points, okay, if you want vacua or basically places where things don't move, okay? And this local stability, or which is called Lyapunov stability, is actually defined in a very intuitive way. So suppose I want that these 2 solutions, so basically I pick up one solution, then I ask for all other solutions, which I want to be close by some norm, infinitely in all times, you know, like for infinite times in the future. And I say that by this norm, it should be, let's say, distance delta, okay? And this delta can be arbitrarily small. So if for each delta, I can find initial data and some moment of time in the beginning, such that all these solutions will remain delta close. So basically, I find distance epsilon. In that case, the system is called Lyapunov stable. So you see, it's a local question, right? So it does not mean that, you know, you need to ask how many solutions can you take. Maybe if you go far away, then you will never stay anymore close to this given solution, right? So you may departure from there. So it's kind of like this can create islands for, if you want, basins of attractor or basins of stability for a given solution. Okay, so now let me remind you what is Ostrogradsky theorem. And Ostrogradsky's theorem, it's, you see, like he would be surprised, but one can formulate it in the kind of modern version for poor people. You write a propagator, which is just now not quadratic, but quartic. And this propagator you can expand, of course, in 2 propagators, right? Just writing standard expression for basically expanding the denominator. And then the key point is that with necessities, I will be this minus. And you see, Mikhail Ostrogradsky would be shocked to see such a discussion. So what he wrote in this French paper, the paper in French, was of course different. And this we can formulate in the following way. So suppose you take a Lagrangian, which depends not only on velocities, but also on accelerations, okay? In that case, what Ostrogradsky suggested that you need to introduce momentum corresponding to your first configuration coordinate, namely q, right? You need to introduce momentum, which is not just dl over dq dot, right, as you would do in systems without high derivatives. But you need also to subtract the derivative in time from derivative of this Lagrangian with respect to acceleration. So you see, it's a kind of non-trivial procedure because that implies that this conjugated momentum, which is conjugated for q, actually involves with necessity third derivatives. Okay? And this is what makes it non-trivial, because you would think that conjugated pairs, that they are related, of course, momentum and coordinate, but momentum is kind of, in some sense, velocity, right? But in reality, what is related here is velocity of acceleration with your first coordinate. So in reality, if you do it for arbitrary number of derivatives, actually it will be the highest derivative before the last one in your equations of motion. So you see, here equations of motion will be fourth order, and therefore the one before last is basically third order. Then what is more non-trivial, he says you that the velocity, which you would think is kind of related to momentum, which is conjugated to position, is actually a canonical momentum. Okay, so that's highly non-trivial. So basically, he's saying that this canonical velocity is actually position. Okay, and if you write momentum, it's just derivative with respect to acceleration. And after that, you do standard formula, P1 Q1 dot plus P2 Q2 dot. And here you need to express Q1 and Q2 dots from as momentum expressions. And if you do that, you will see that your Hamiltonian actually does not depend on this P1, right? So basically, it only depends, linearly on P1, but other parts, they're independent on P1. And this is highly non-trivial because your Lagrangian, right, it was not dependent on third derivative of q, on, if you want, velocity of acceleration. So therefore, you know, this Hamiltonian doesn't depend on P1 except of the first term. And this is a famous Ostrogradsky so-called instability, because you see, this Hamiltonian is with necessity linear in P1, so it's unbounded from both above and below. So there are different ways how you could potentially fight with this. So either you introduce non-trivial topology for P1, maybe. In that case, the Hamiltonian will be bounded, okay? Another option is to say that this P1 is conserved. And that's another potential, you know, opportunity. So basically, yes, you abuse it, you have it like arbitrary negative, but somehow then you would need to write all interactions in such a way that this P1 is conserved. Okay, in that case, dynamically you would not be able to abuse this unbounded from below. But this is tricky, as you see. Good. Now, if I give you the simplest example, this is very well known as Spice-Uhlenbeck oscillator. It's kind of version of it, if you want. So I take normal oscillator with frequency 1, mass 1, then I add this second derivative squared. Then I do what Ostrogradsky told us to do and plug it in. What I will obtain is the following Hamiltonian, okay? So in this Hamiltonian, it looks like a bit odd, but whatever. I can now introduce canonical transformation, and out of this canonical transformation, I get a Hamiltonian when you see that one of the momenta, one of the, if you want, masses have a negative sign. Okay, on itself, it's nothing really horrible because the system is quadratic. I could calculate everything, so no reason to worry. But if I add whatever non-trivial interactions, high order terms, that would be a disaster. Okay, naively, one could expect at least that. So you see, if you look at oscillator, so one can write it in this way, and then in this oscillator, it's a question whether mass is negative or positive. So that basically defines the sign of p squared. We can also compare it with the action for, let's say, cosmological perturbations. And there are two free parameters usually, the sound speed, and if you want normalization in front of naive Lagrangian. And this, in most actually normal applications, this is not this capital Z, but small z squared, okay? So, but here, if you look at the Hamiltonian given mode, then it looks like, if you compare it with the formula above, like a normal oscillator, where this normalization plays the role of the mass, okay? Now you can see that if I take this mass to be negative, then it's a ghost, okay? On the other hand, if I take this omega, which is now cs squared k squared, to be negative, then this is what is called elliptic system or gradient instability. Okay, so now coming back to this ghost and gradient instabilities, so you see gradient instability is sound speed less than 0, and the ghost instability is actually this z less than 0. So gradient instabilities are bad because already on linear analysis you see exponential growth. And as you see, this exponential growth has a rate which is faster with smaller k, sorry, larger k. So the larger is the k, the higher is the rate of this instability. And that you see just in linear analysis. So the only way to avoid it is to assume that somehow your dispersion relation changes, and then the other terms, let's say k to the 4 into omega. So basically omega squared is some cs k squared and then plus k to the 4. For some systems it's possible to have, but it's only worse for very small c. Then there is this ghost story when z is less than 0, and that doesn't give you any troubles in linear equations. You will not see any instability. As you see, the z is in front of everything. So, however, what it does you basically does give you a instability in interaction system. So basically, if you look, let's say, at Feynman diagram in this most simplest case, you can produce two of these perturbations out of vacuum. And of course, you care about gravity, so therefore these perturbations, these ghosts, are connected to, let's say, photons through some graviton, right? In the simplest situation, when the z is just -1, and you kind of assume that they interact in a standard fashion, in each of these vertices, right, you would get 1 over m Planck. Therefore, this whole amplitude is 1 over m Planck squared, and therefore the probability is 1 over m Planck to the 4. So now that implies that rate per unit time, per unit space, should be 1 over m Planck to the 4, and then you need to, by dimensional reasons, you need to find somewhere dimension full parameter and put it power 8. Okay, and the meaning of the dimensional full parameter would be actually the cutoff on external momentum. Okay, and that's what was estimated by Klein and company in 2003, already more than 20 years ago. So the interesting thing is, if you try to do it in Lorentz invariant setup, so basically you see this like incoming momentum cutoff, it's not a loop cutoff, right? Then the whole thing diverges. So therefore, you need to kind of assume that you introduce symmetry breaking or whatever, some stroke coupling scale in a Lorentz non-invariant fashion for that. Okay, so after saying that, you know, like how we can understand this instability, basically you have kind of scissors of normal matter, ghosty matter, total energy will be conserved. When time elapses, you get, you know, the scissors are opening because they normally interact, and the normal matter increases energy, the ghosty matter decreases energy, total energy remains constant. And what is the key point there? The key point is the interaction, which is this nail, okay? And the question is, are there such nails which prevent the scissors from opening? Okay, that's if you want the issue. So, but first, let's see how unstable can it be. Let's take normal oscillator. Let's couple this normal oscillator with ghosty oscillator, you see wrong sign, through normal quartic coupling. And then we just plot, let's say, from some initial data, which looks like almost vacuum, we plot energy of this first term. Okay, so basically energy without interactions of the first guy, which was normal guy. And here it's a logarithm of this energy. And as you see, the growth is quite substantial, just 10 periods of oscillations and you are out, okay? What is more interesting is that I could make coupling constant smaller, and if I do that, then I can postpone the appearance of this instability to quite late times. And this is what quite interesting, but you see this instability is still super strong, okay? But it may happen quite late in your evolution. And this is actually a non-trivial fact about this ghost instabilities. So if you run everything numerically, for small coupling constants, you may not have enough time to find the onset of this instability, okay? And you could conclude that the system may be stable, but in reality, you just have not waited enough time. Okay, so therefore it's quite a dangerous instability, which could be quite surprising for many results. So basically, the tacit out of the story is that don't believe to just simple numerical simulations there, because not only that they take particular initial values, but also maybe they have not waited enough. So basically, numerical statements are not enough to say that the system is stable. Okay, so now, you know, you can also consider more how unstable the things are, and that's, I hope we will finish this paper very soon, probably this March. So we took just two field theories and 1 + 1 dimensions, and this field chi we consider to be a ghost. So you see, what is very interesting is the following, that here we use signature convention plus, minus, 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 so therefore phi is a normal field, chi is a ghost, okay? However, if I now write equations of motion, then what I see that this sigma can be brought to my potential term. So that automatically implies that the Cauchy problem is well posed and that there are no instantaneous instabilities. Because well posed Cauchy problem implies that the growth is bounded by some universal k-independent constant, okay? So that basically means that this instability can be physical one, okay? So maybe in some systems, you can experience this instability. It may be even quite benign. It's not necessarily that dangerous. So, you know, this is a results of how these two fields would evolve. You know, one can see how different energies would increase. So here there is still some instability, but you see, it's not a big deal. If you check, they can be quite long-lived, okay? So now, what is our stable PRL model? This is very simple story. So you take normal oscillator, ghosty oscillator, the interactions, okay? So now we suggested these strange interactions, okay? It's not horrible, you know, it's just a bit non-polynomial, but it's a normal analytic function, no, nothing bad. And you have one coupling constant there. So the good thing is that you see, this potential is actually bounded. So if you take coupling constant away, this function is always less by absolute values than 1, okay? So it's just from 0 to 1. And then if your coupling constant is negative, it will be from -1 to 0, okay? So you can rewrite this potential in this way. It doesn't matter. And then you can write total interaction potential, and you plot it. And you plot it for absolute value of lambda less than 1/2 and for absolute values of lambda larger than 1/2, okay? As you see, it's a kind of funny potential because it's kind of either one saddle or two saddles, okay? And if you expand it around 0, then you would see that, okay, in the first case, when lambda is less than 1/2, linearly, both frequencies are actually less than, I mean, they're positive, right? They're not imaginary. So in that sense, from linear perspective, you would see that surprisingly, the saddle is actually linearly stable. But you see, linear stability completely avoids all issues related to ghosts, as you have seen on the previous example. So therefore, linear stability analysis is not sufficient to claim that there is stability for such systems. So you see, in reality, it is true, and that's what I'm going to show you, that the saddle points are actually stable, okay? So they will be Lyapunov stable with nonlinear proof. And moreover, what one can also prove that the motion for all trajectories there, for all initial data, is Lagrange stable. So basically, it's finite. Okay, so now you can see numerical solutions. You see boring oscillations. You can see a plot. Unfortunately, I cannot plot four-dimensional things. So in 2D, it looks like a donut. And time evolves from red to blue. But you see, it's kind of oscillates. Nothing particular is happening. You can also look at Lissajous figure. So XY configuration space, how the trajectory covers some shape. Okay. And if I waited not 500 periods, but longer, let's say 10,000, it will be just covered, like just colored pillow, okay? So it looks like stable, you see, but as I showed you before, numerics can be actually cheating you, and it can be tricky. So the question is, if I claim that it's stable, why is it stable? And actually, what is the black magic behind it? And by the way, I took this picture not far from Prague. So it's actually the point that there is a first integral in the system. And that's, if you want, power of imagination. So there is this guy, this E, which is actually conserved. Okay? And that you can just check explicitly. But how we can get it, we took a system which was written for normal fields, right? For normal, oscillators, if you want, for positive masses. And then we have done imaginary canonical transformation. So therefore, that's power of imagination. And by doing that, we created a system with one ghost, but still an integral of motion. Okay? And that was a result by Darboux. And actually, it turned out that even before it was studied by Liouville in this paper. Okay? So you see, it's all very, very fresh, like as you can imagine. Good. So interestingly enough, this symmetry is probably kind of accidental. So actually, so the conservation of this integral of motion is not related to real kind of symmetry. It's probably kind of like what happens usually in geodesics if you have Killing tensor, not Killing vector. So then this first integral you can write in this way, where this sigma, it's actually this weird kind of like, if you want hyperbolic rotation operator squared, then plus 1/2 of the norm of the radius vector in your phase space. Okay. And then what can you see? That you see, if I write my first integral in this way, then what do I see is that actually this y squared minus x squared multiplied with interaction potential, this is always also bounded. Okay, just if you look at the form of the potential, you see it very easily, right? Because it's same expression y squared minus x squared plus 1 plus y squared x squared. So this is a positive 6, okay? So therefore, for all times, this integral of motion, it's always larger than this radius vector squared plus a positive bit, which is this k squared, right? And minus this interaction constant by absolute value. And it's always less than the same radius vector squared plus same k squared. So sigma is always positive, plus this coupling constant. Okay? And this looks like not sufficient to prove anything. However, if now you look that this E is actually this integral of motion, then what you will see is that at some initial moment of time, this E is larger than sigma minus lambda and sigma and smaller than sigma plus lambda, right? So this is these two boundaries. If you want, this was your donut, right? But if you write the same thing in later times, right, then what you would obtain is that this radius vector at later time is larger than the radius vector squared previous time minus 2 lambda, and the same thing from, if you do the opposite. So therefore, what you see that at every later moment of time, this expression for sigma, it's between the same sigma which was early time minus 2 lambda by absolute value, and sine sigma plus 2 lambda. Okay? So in particular, if your original sigma was, if you want, of the order of like basically smaller than 2 lambda, then you move into kind of sphere, right? But if your sigma is larger than 2 lambda, then you move in a kind of shell. It's kind of onion shell, okay? Then you are restricted. So basically you have smallest value of sigma and largest value of sigma. But sigma was the radius vector plus something positive, okay? So that explains this thing what you have seen before, and that gives you analytic proof that the motion is always finite. And you see, it's always finite, doesn't matter whether lambda is larger than 1/2, smaller than 1/2, it just doesn't matter. So basically, the system always evolves in a finite region of phase space. That's a nice proof. Then you could say also about Lyapunov stability, you can look at this integral of motion, and you can check that it satisfies the conditions, that in the origin, it is 0. Then, of course, for this product to be positive, this E is also positive. And if you take it negative, you can see that it's always larger, this E, than some positive guy, provided that, of course, lambda is less than 1/2 by absolute value. And that implies that this is what is called second method of stability. And this integral of motion can be considered as a Lyapunov function. So this Lyapunov function cannot grow with time because it stays constant. It's 0 in the origin, and it is positive everywhere except of origin. So that implies that for lambda less than 1/2, the origin is Lyapunov stable. Okay? And this is a nonlinear proof. That's important. So the thing is, one could do the same proof for these two other saddle points for lambda larger than 1/2. And that implies it's a very interesting situation, especially for the second case, that your origin is linearly unstable. Nevertheless, the motion is always finite. And moreover, you have two other stable vectors. Okay? So look, then you can realize the system through higher derivatives. This is not very exciting, but you can write basically Lagrange with acceleration and see that this model is exactly the same thing. Some people were complaining that, oh, why it is interesting? You obtain the system through complex canonical transformation. Probably due to analyticity, you preserve some properties of motion. So therefore, it's not a true ghost, but some particular ghost, and just this particular ghost is funny, but in general, it doesn't mean anything. But you see, so what you can see is that like what we care is in reality global properties of motion, even more than local. And therefore, had I done this canonical transformation on a very simple system, p² plus cosinus hyperbolicus, okay? In that case, we know what's the phase space. That's on the right, right? And all trajectories are just bounded normal orbits, right? That's just very simple thing. However, had I done this canonical transformation, I would obtain, if you want, kind of axionic potentials of cosinus instead of hyperbolic cosinus, normal cosinus, and wrong sign. This is this ghosty sign. Of course, for 1 degree of freedom, it doesn't matter whether it's ghosty or not. It's basically irrelevant. However, what happens with the motion? If I want to have complete equivalence, for this Hamiltonian, I would need to take imaginary initial data. if I take real data, it's not the same phase space. The phase space looks like this. And of course, global properties are completely different, as you can see. So in the first example, all trajectories were finite. So the motion was always bounded for all initial data. In the second example, clearly, the blue trajectory is infinite, right? So it's not bounded. Okay. So now the thing is that you can generalize the situation. You see, that was a kind of bit particular potential, and you could say, okay, are there like something more natural which one could do? So the point is that you can take the whole class suggested by Liouville. I don't know why we have taken this abbreviation LV, but basically the point is that these systems with this type of potential, where U is given by this, you don't need to recall what is this. But the important thing is that for such systems, we can show generic conditions for this global stability, okay, for Laplace stability. And the conditions are that this C in all these expressions is positive, that these two functions are actually bounded from below, these arbitrary functions f and g, so it's very general, and that this f and g far away, like basically at infinity, should grow, and they should grow faster than if you want the squares of this u and v. And u and v are kind of, if you want, hyperbolic coordinates, or if you want imaginary version of elliptic coordinates, okay? So, but basically these simple conditions, they provide you stability. How come? Well, because you can use what is called usually Lagrange-Dirichlet theory, and what it says is that the minimum of energy is stable, right? Here, of course, what happens is again the same like magic. So you have for this particular Liouville system, you have integral of motion. This integral of motion has a structure of, if you want, kind of positive kinetic energy and potential energy, okay? And the point is that, you see, if you care about Lagrange-Dirichlet theorem, you don't need to know that it's energy. So it's whatever integral of motion would work. So therefore, now if our kinetic energy is positive definite, and that you see that's the requirement for C to be positive, that implies that minima of U would give you stable equilibrium points. And if U is actually growing at infinity, that gives you a potential trap. So you cannot escape from there. Okay, so what is interesting is that following these ideas, we were able to do the following. You take a particular type of functions f and g, thinking that they are just polynomials with the same coefficients. So if you do that, then suddenly you realize that you can prove that the lowest order of such polynomials, when you have this potential trap, where under potential, I mean the potential part of integral of motion, then the simplest potential in normal Hamiltonian is this guy, and it corresponds to potential in the integral of motion, which is u. So you see, v is potential in the Hamiltonian, u is potential in my integral of motion. And you see, it's nothing really bad. It's just sixth-order polynomial with some particular coefficients. And the good thing is that this polynomial produces u potential trap. So therefore, you cannot escape. So the motion will be globally stable. So you see, you can investigate it a bit more. You can plot it. And as you see, I plot this potential part of the integral of motion. And it looks like a very complicated shape with clear minima. So you see, basically here in the first plot, there will be 4 absolute minima, symmetric. And black dot in the middle is also a minimum, but it's not the absolute minimum. If you change some parameters, it can look differently. For example, it could look like these 2 plots on the right. And basically, you can investigate parameters, and it's nice to parameterize them in these normalized frequencies. So you see, this C4 is supposed to be positive just in order to create your potential well, right? And then depending on ratio between these two normalized frequencies, capital omega x and capital omega y, you are either in the situation which we denoted as 1, so that's when you have 4 minima, or in situation when you have 3 minima, or in situation when you have just 1 minimum. Okay, and this is quite interesting because you see, it seems that kind of interaction with ghosts creates, or if you want, shifts some vacuum which you want to have. Actually, minima of U are actually saddle points of V. Okay, that's another thing what we showed in this new paper. I mean, second one, what I mentioned. Then you can look at the motion. You see the motion looks like very similar to what we studied before. So basically, it's a pillow. This shape of the pillow is given by shape of your potential for the integral of motion. And basically, the motion is bounded there. You cannot do anything. You can, look at either xy or px, py. You can even do a different thing. You can destabilize the origin. But nevertheless, because your conditions were only in this potential, in this polynomial case, on C4 and C, you see that the motion is kind of more funny, but nevertheless it's bounded. It's much more chaotic, much more complicated, but it's also always bounded motion. And you see, you may say, okay, but what's the deal? I mean, like you provided some system with some integral of motion. Maybe it's not very natural. Who cares? It's very particular. But you see, the important thing is that the Kolmogorov-Arnold-Moser theorem tells us that if you have an integrable system which is stable so that the motion is finite there, that implies that there exists what is called action angle coordinates such that the motion happens on tori. Okay? And then if you add any structural changes to the Hamiltonian of the system so that it ceases to be integrable, nevertheless, what it does, if the changes are small, it just deforms the tori. And up to measure 0 of all solutions, you just continue to move on this tori, so the motion is still finite. Okay? And this is a great result. This is very interesting. It may actually be not the case for higher dimensional systems, but that's a different story. Okay? So basically, the major equation in that case is the following. So are there such systems in nature? Okay? That's actually what is interesting. So usually people say that these ghosts are not there just because, the whole thing is unstable and we don't want to have it like as unstable. So therefore, we should disregard them. But this example shows you that actually there is this infinity of systems which are definitely stable. Okay? And which are stable in all senses, in global sense and in local sense. So basically, they Walker or Lyapunov stable, the global solutions are always bounded. So therefore, stability cannot be the reason why these ghosts are not there. Okay? Maybe there are, but we're never brave enough, we never dare to actually model something with ghosts. Okay? So yeah, I think it's very interesting. So one can try to find other like real physical systems where probably ghosts could model something. One could try to investigate better instabilities for many degrees of freedom and so on. I think it's all open questions. So by saying that, so thanks a lot for your attention, and I'm looking forward to your questions.
Thank you, Alex, for the nice talk. Are there any questions?
Oh, hello, can you hear me?
Yes,
Yeah.
we can.
Yeah. Hi, Alex. This is nice talk. My question is, this ghost can be mapped to or the analogous to the dark matter?
Yeah, actually,
Because
see, the thing is, it's actually funny because we just had a talk by a young student of Luc Blanchet, and these guys in Paris are brave enough to consider, if you want, gravitational polarization. And that implies that, you see, you need kind of dipoles gravitational dipoles. But dipoles, that implies that you have positive mass and negative mass, right? And they try to model dark matter using that. And if you think, it's kind of interesting, because if you have such dipoles, you would have negative, if you want, susceptibility, I think it's called, right? Because think of the one way. Imagine you have gravitational dipoles, right? Then for normal dipoles, positive charge will attract negative charge. So therefore, effectively, the charge will decrease. For gravitational dipoles, you have positive mass, and it will attract positive mass, right? So therefore, the charge will actually increase, right? So, and that what actually gives them a hope to model dark matter and things like that. Though they need to keep these positive and negative masses together. If you want, the ghost and the normal mass should be confined. Then actually, Jim Klein was brave enough to consider boosts of phantom dark matter and things like that. You can check his papers. So he was doing dark matter with that. But you see, that's a bit tricky, because formally speaking, your like where it's interesting is when this W is less than -1, right? That's interesting for cosmology. But for dark matter, we need W approximately 0. So that's the interesting story. But yes, people tried to do dark matter with ghosts.
But another question is that if the gravitational dipole is exist in your ghost theory, so can be this mass can be analogous or some simplified version of the Bondi mass, because the gravitational dipole is basically exist in Bondi theory or Bondi mass. I remember that.
Mm-hmm. Now you see, these guys, they model these dipoles, but it's not really clear how to consider, basically these particles without confinement. So in reality, what you need, because you see, Bondi dipole would always, it's a funny thing. I don't know, guys, whether you like, except of Gautam, whether other guys would know what Bondi dipole is. So Bondi entertains this idea about having positive and negative masses. Imagine that the masses are the same and they interact only gravitationally. That's important. In that case, so there is positive mass, there is negative mass, and positive mass, it's repelled from negative one, right? So therefore, that will be the acceleration of the positive mass, right? Pointing out here. Now you take negative mass is also repelled from positive mass. So formally speaking, it gets a force here, right? This way. But because it has negative mass, so the force gives you acceleration in the same way. So basically, whole dipole is accelerating without any bounds in the direction of the positive mass. But you see, that happens if there are no other forces. But of course, if there is another force which kind of holds the whole thing together, that's not anymore accelerating, most probably. But that's, I think it's a very, very interesting question to investigate. What does it mean? Because you see, again, if you can control gravity by screening it, it's like abilities of gods.
Thank you.
So Gautam, have I answered your questions now? Question or not?
Yeah.
Okay,
I understand.
Yeah, the other questions? I guess, Cheo, you already turned your camera on.
Yes, I do have a question. Thank you very much, Alex. So if I understand correctly, like in your method, if you want to have a stable dynamical system with negative kinetic energy, the interaction has to be assigned properly such that it satisfies the criteria that you put on your slides, right? So can you elaborate more on how to interpret that particular criteria? I still don't quite understand.
Well, you see, in normal circumstances, you also need to have some particular interaction to have stability, because if you write generic interactions, you will get a lot of whatever, at least tachyonic instabilities, or you could get potentials which are unbounded from below and things like that, right? So there are always criteria on interactions. Just here with this Gauss, these criteria are more subtle in some sense, right? So basically, would be nice to have generic criteria. So without this second integral of motion. But I don't know how to write, like whether they exist and how to write them. Because you see, we kind of so got used to energy, and that the energy for normal systems is positive definite, and that's what what is binding the motion. That this is for free, right? This is amazing. But for these systems, it's not for free. This energy doesn't help you at all. Okay. And then, yeah, it's the question how to get some other maybe integrals of motion or some other things which would bind the motion. But it's not trivial, because you see, if you go beyond integrals of motion, which are also binding, I don't know how you can get results on global stability. So you see, probably you could, I don't know, take some systems. In some systems, you can find some basically fixed points or vacua. For this vacua, you could first analyze linear stability. They can be linearly stable. And then you can try to do perturbation theory, okay? And for perturbation theory, you may find that either they are stable or they are actually kind of metastable, okay? So formally speaking, that's the way to go, right?
Yeah.
This will only give you a region in phase space, right? When it is kind of stable. And whether it's globally stable, you would not know. Because I see here, the key point is absence of global runaways, that the motion is always trapped, always finite. Why it is the key? Because that actually, I can give you a kind of, hint. So that allows you to quantize this too. Because if the motion can leak to infinity, you cannot truly quantize it. You need to put it in a box or do something.
Yeah, sure.
So that's the key point. So you need this global stability, or Lagrange stability. This is super important if you want to have well-defined Hilbert space.
Sure.
And that's what we have.
Yeah. Okay, thank you.
You're welcome.
Any other questions?
By the way, you guys founded this seminar series of this intergalactic seminars like after COVID or during COVID?
Last year.
Oh, last year only. Okay. Okay. No, it's still nice.
Yeah, maybe if there are no questions, we can stop the recording.
Sure.
Sorry.
Thank you very much again.